The right to be forgotten is a 21st century right that many believe humans have to be deleted from the internet or various electronic databases. Now, there's all sorts of memes about deleting the internet and how difficult that would be, but in principle, it's certainly possible to take a bit of information and apply some procedure, and let's suppose that it's in the context of some other data, so we want that data to remain intact, but we want the bit to go to some fixed state. So all bits that enter into this device end up as 0, and other data that might be in the device remains intact. That's in principle possible to do. However, it comes at a cost. So this is a rabbit hole that you'll certainly find lots of other YouTube videos about, Wikipedia pages, if you want to go down. I only mention it because it's historically interesting that when researchers were thinking about the physical limitations on computation, including irreversible computation, which includes things like deleting information or performing like an AND gate where computational paths combine, that led actually to quantum computing. That's beyond the scope of this subject, but it's an interesting aside. The same question can be phrased in the context of quantum information, and so that hypothetical circuit would look the same. I have some quantum state, and it is in some quantum memory, in some quantum computer, and the rest of the physical system is in some other state. And what I want to happen is that state to be erased. So all potential quantum states go to the same 0 state, and the rest of the memory remains intact. Let's call this D, and that's the delete operation. So can that be done? Well, we can play the same game that we played in the last video, which was about cloning, where I wanted to take a state and create 2 copies of it. This is almost the inverse of that, but we can look at the same sort of analysis where we said this D operation, which looks like something that takes psi phi and produces 0 phi, has to apply to every quantum state. So let's say take another state, call it omega phi, and that also has to go to 0 phi. So again, we have these 2 equations. In order for them to be satisfied, for example, the inner product of the left-hand side has to equal the inner product of the right-hand side. So let's look at the left-hand sides, and let's take the complex conjugate of the second equation. So we have phi, we have omega phi d star, then d omega, this is the first vector, d psi phi. Okay, so I've taken the second equation and looked at the inner product of that with the first equation, and just like when we looked at the no cloning theorem, this is equal to the identity, and so we end up with the inner product of omega and psi and phi, and the inner product of any vector with itself is the norm, which is normalized for quantum states, so that's 1. So I end up with this inner product here. What about the right-hand side? So the right-hand side is easier. I just have the inner product of 0 phi with 0 phi, which is 0, 0 inner product and phi phi inner product. Those are both 1 since everything's normalized. So that thing is equal to 1. And what this implies is that the inner product of omega and phi, sorry, omega and psi, is equal to 1. So in fact, I can only delete one vector. There's no single operation, no single quantum gate or circuit or algorithm that takes an arbitrary quantum state and deletes that by taking it to the same 0 state. What this is saying is that if I want to do it for 2, the second one has to be the same as the first one. Okay, so we can't create a circuit that works for a single state. But perhaps this circuit here that we wrote down was a bit too rigid. Now I have a quantum state, I have some data sitting around, but also maybe I have some other data which, I don't really care about what happens to. So that certainly needs to be deleted. Some parts of the memory has to stay intact, but this thing can go to some new state that might depend on psi, that I don't really care if that gets changed in the process of deleting the original information. Alright, so again, let's call this D. So we have delete, same, and that's some trash that we don't care about. So D applied to psi, phi, g can be decomposed by looking at psi in some basis. So let's take the computational basis. And remember, we're just considering qubits. So I have D, we'll write this out explicitly. So I have D, and that's acting on alpha 0 phi g plus beta 1 phi g. So I've just expanded the psi vector in some basis. And now D distributes to the sum, and I get alpha D0 phi g plus beta D1 phi g. And you can see that I'm making extremely efficient use of Dirac notation here by suppressing all of the kets into 1. Now I apply the D operation. So what the D operation does is take everything in that first entry to 0. So I have alpha 0 phi, and the g could depend on what that state was. So g might depend on 0, depend on it being 0. And now I get 0 again because I'm deleting that bit, and I get phi and g that might depend on what the original state was, the one state. Okay, so now we notice that there's some common factors here in this tensor product, so let's pull those out. So let's pull out 0. I'll write it out explicitly here, just to be clear. So I'm pulling out those two factors, and that means that, well, but let's put the tensor into just to be extremely explicit. So I've pulled out those two factors, and then the last position is the thing on the far right of the tensor product, and that's everything that's left over. So that's alpha G0 plus beta G1. Okay, And if I wanted to write that out in the very compact notation, I would write 0 phi and then suppress that third one as well, but I can't really suppress the notation again inside of the bracket. Beta G1. Alright. Okay. Now, this looks like it's done the trick. I've taken an arbitrary vector psi and I've produced something that has that the state in that position now 0, so it's taken any vector and produced 0, which is what we want, and phi stays the same, which is what we want, and we're left with some garbage that's sitting there, which we said we didn't care about. Okay. Not bad. But we'll notice that this alpha G0 plus beta G1 looks a lot like alpha 0 plus beta 1. In fact, if G0 is 0 and G1 is 1, then, so let's write that out. If G0, we'll put some cats on it, and G1 is 1, then all that's happened has been I've just swapped the state out of the first location and put it into the last location. So this original state gets mapped to 0. Yeah, that's what we wanted in the first quantum register. And the second register stays the same, but the third register has psi in it. So I haven't deleted the information at all. I've just moved it somewhere within the quantum memory. Okay, so is that 0 and 1? Not necessarily, but I can still recover the quantum information that was in the first register if G0 and G1 are orthogonal. So I can map back from that orthogonal basis to the original computational basis, and I have the exact same state. So this state contains the same information as the original one, the alpha and beta, which I can extract by performing a measurement in the G0, G1 basis, or mapping it back to the computational basis and doing one of our standard measurements. But that's only true if G0 and G1 are orthogonal. So let's have a look. G0, G1, all right. That is not what we want to do, actually. Let's look at this whole vector. Give it a name. Let's name this vector capital G. And let's look at the norm of capital G, which we know should be 1. Okay? So what is the norm of capital G? It's the inner product of G with itself. So I have alpha star, and then the broad G0 plus beta star, and then the broad G1. And that is going to be taken as inner product with itself. G0 plus beta G1. Okay, so I get 4 terms. I get alpha star alpha, which is the modulus of alpha squared, and that has a G0, G0. Okay, and then I have alpha star beta, and that's G0 with G1. And then I have a beta star alpha, and that's G1 with G0. Good. One more term. It's getting long. Beta star beta, which is modulus of beta squared. And then I have G1 inner product of G1. Okay, so many of these disappear. That's normalized. That's normalized. And you'll notice that this is in fact the complex conjugate of the term next to it. If that thing is alpha beta star G1 G0 complex conjugate transpose. So just to be explicit here, let's call this X. And so these two terms here are X complex conjugate transpose plus X, which is just twice the real part of X. So if I take a number, I add its complex conjugate to the original number, then the imaginary parts cancel, and I'm left with twice the real part. So now this big complicated mess reduces to something much simpler. So in the first term I have alpha modulus squared. The last term, I'll put that next to it, beta modulus squared. And then I have twice the real part of this alpha beta star inner product of G1, G0, which was what we were trying to get at originally. We want to show that this has to be 0. And we're almost there because this is 1. The original state was normalized. So we have 1 coming all the way up from the top here. Right, we have that 1. And that is equal to 1 plus the real part of this number, which is inside of this argument here. Okay, so 1 equals 1 plus something. That extra something has to be 0. So this has to equal 0. And alpha might be 0, in which case I'm just trying to delete 0. Beta might be 0, in which case I'm just trying to delete 1. We know we can do that, so without loss of generality, let's assume that alpha and beta aren't 0, which means that G1, G0 has to equal 0. Which is what we wanted to show, which means that in this deleting circuit here, I have removed the quantum information from the first register, but I've just put it into the third register. So I can't delete information. There's no quantum paper shredder. There is no, you can have the right to be forgotten, but if you're a quantum robot, that right is impossible to enforce. Is the no deleting theorem. Okay, so that's the last module of this week's lecture. So we had Halevo's theorem, which said that we can't store exponential amount of information inside of a qubit. We had the no cloning theorem, which said we can't copy information. And now we have the no deleting theorem, which says we can't delete information. These things point to a conservation of quantum information. So quantum information, you can't double it, you can't copy it, and you can't remove it, you can't delete it, so it has to be conserved. There are lots of other similar results, so these are called no-go theorems, and usually they're phrased as a request of some sort of quantum circuit or algorithm to do something that we might expect quantum information should be able to achieve from the intuition that it can trivially be achieved with classical data, and we have this suspicion that quantum data is somehow more powerful or allows more possibilities. But in many cases it allows much fewer possibilities. So again, think about you watched me in this lecture delete a whole bunch of things, erasing things with my virtual pen. Well, I wouldn't be able to do that with quantum data, not with a unitary circuit. So I could push all of that data to some other part of the computer, but eventually it would all get filled up, and I would have to do the same thing that we do in conventional computing, which is somehow remove entropy, which would impose some thermodynamic cost. Okay, so next week we're going to start to look at some canonical quantum circuits, and a little bit more positive than this week, and really start to look at what we can do beyond classical information, in spite of the things that we can't do with quantum information.